Okay, so I will be taking that remote sensing part especially. Okay, uh, I hope your progression of the syllabus is according to the plan which is going on. Okay, we're ready to go here. So this is part of surveying and geomatics, greater part of surveying. So what do you do with surveying? What is your understanding of surveying so far? Why you need to do surveying? What is surveying? Hmm? Okay, so those questions were likely questions I think you should be knowing by now. Anyway, uh, go and then see what madam has been teaching you so long. My thing is now I'll be concentrating mostly on remote sensing. So remote sensing is basically the two words that you see on the screen. First one is known as remote, another one is known as sensing. So what do you understand by remote? Remote. I will go very fast, okay? You have to really take participation in the class. Otherwise, it will be difficult for you to cope up. What is your understanding of remote when you hear the word remote?
It's far away.
That's good. So something is remote. Remote means you are not really in contact with the object. You are somewhere at a distance from the object. Okay? And then what is sensing in that case? Sensing means you try to feel whatever parameters that you are interested in. So, knowingly or unknowingly, actually, we have been conducting remote sensing as human bodies through our five sensory organs. So, what are the sensory organs that we have in our body? First one is our eyes. Okay, so when you look through your eyes, you see something and you then make your perception of that object. But you do not really have to be in touch with that object. Your eyes did not have to be in touch with that particular object. Is it? So, in that way, your eyes are remote sensors. Then, what are the other sensors that we have in our body? How about our tongue? So, with the tongue, we taste. So, unless we keep the food in the mouth or in the tongue, we cannot get the feel of taste. So, from that point of view, the tongue is not a remote sensor. Tongue is a non-remote sensor. How about the skin? So with the skin, you know how cold or how hot, okay? And then for that, you can do it from a distance. So it is also a kind of remote sensor. Then your ears, if you're listening to a music, you can listen or hear it from a distance. That is also a remote sensor. Then with your nose, you smell. So if there, unless someone has COVID, you lose the sense of smelling. But without it, you can smell anything or something from a distance, isn't it? So your nose is also a remote sensor. So knowingly or unknowingly, we have been doing remote sensing uh, for our body with the five sensors that we have, except one, that is the tongue. So you're remaining with the four sensors. So remote sensing as a science or as an art, also you can say it just portrays or mimics the same thing. That means you try to get an understanding of something, but you do not come in contact with that particular object. So where we do it then? So we do it using the satellites. So the satellites we fly to the outer space, and then from there the satellites are equipped with some cameras, and then those cameras they monitor the art at some constant interval of time. And from there, we can analyze various properties which are of our own interest of the surface of the earth. So that is a kind of remote sensor. So if you are building same kind of a sensor and then mounting it on a balloon, or suppose a hot air balloon, and then the hot air balloon is flying above the earth, and at the same time it is capturing photographs, that will also be a remote sensor, or then that will also be under the purview of remote sensing. Or if you are mounting some kind of a camera on your motorbike and then you were driving it across the streets in your hometown, taking photographs, the same as remote sensing. You are doing remote sensing. So if you are looking at the Google Street View nowadays, what do you see? You see three-dimensional objects on both sides, which are actually captured by cameras mounted on bicycles. So these are all parts of remote sensing. Even from the ships, which may be sailing at the seas, and then these are equipped with some cameras mounted on the top of the ships, then they are taking photographs, they are doing remote sensing. So by definition, remote sensing is anything getting or acquiring the parameters of a particular object without directly being in contact with the object. So in terms of the science, it is a fairly new concept, okay? And then initially remote sensing was used for military purpose. It was not used for civilian purpose. So there is a very interesting history behind remote sensing. Why or how the science has progressed over the years so rapidly. So before the World War ended, that means the 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 Second World War ended in 1945 with the dropping of the atomic bomb in Hiroshima and Nagasaki. Uh, the war has actually seen a lot of turmoil, and then with the ending of the war, these turmoils have never ceased to exist. It means again there were no active wars, but the whole community or the world community has, or they just started to get divided into two groups. One is under the USA, another one is under former Soviet Russia. So among them, the Cold War period has started, and then there were undeclared competitions in every front that were going on. That may be in terms of science, in engineering, in terms of bomb making, in terms of military. So remote sensing also was one of those. And then first experiment was started with the militaries. So first competition was which country actually was able to build a satellite that could be flown to the outer space and then at the same time capture photographs. So it was the Soviet Russia. So it started with the Sputnik satellite. It was in 1950s, okay, just after the war. So since then, this war is going on. It is an undeclared war or the Cold War, and then this contributed to the advancement of this particular science. And actually, the science is opening up for civilian purpose only after 1972. How? In 1972, United States launched the first civilian satellite, which is dedicated for the use of civilians, and the name of the satellite was Landsat, Landsat. Okay, so as I showed you in the last class, you can collect photographs or images of the Earth from 1972 of any place, yeah? uh, completely free of cost. You can go to the internet and then download it. So it has been possible by these series of satellites known as Landsat. So it is a part of remote sensing satellites. So by definition, those definitions, if you see, it mostly have originated in 1976 as Lins and Simonet. And he says that remote sensing is the acquisition of physical data of an object without touch or contact. So this is what we have been discussing. Then again, this is another aspect which is quite hidden in the sense that remote sensing also depends on who is doing. That means, though this is a science, like all other sciences, there is a personal touch to this science, which is also known sometimes as arts. So this depends on who or the person who is actually doing this remote sensing. So depending on who is conducting the analysis may be a little bit different. The style of acquisition of images may be different. The interpretations may be different. And finally, the conclusions may also be somehow different. So that means the highlight is that though it is a science, it is also an art. Okay, so this is actually practically true for all of the sciences. Science is always combined with arts. Arts sets the imagination free. Okay, our science asks to stick with the hard facts. Okay, so this slide that you see is very important, and then I hope you will remember this forever in your life whenever you will be interested to know about or thinking further to go into the study of remote sensing. So remote sensing, I will be shortly saying is RS here. Okay, as you can see it on the screen. So as I said, anything that you can sense without directly being in contact is actually remote sensing. Okay, so on the left hand side of the screen, you see this particular photograph. Just concentrate on this one. There you see the sun. Then we have a satellite. On the satellite, there are inbuilt sensors. And then we have the art. Okay, so why the sun is there? Because the sun is the source of all kinds of energy that you can imagine for life to exist on the solar system or in the earth. So it is continuously emitting this energy, and this energy is coming in the form of waves. So this energy has actually dual nature. If you have studied physics long before, you will understand that sometimes it behaves as packets of energy, which is given by the Planck's given by the photon, or sometimes you can use or you can think of these as some waves or wavelengths representing various or different wavelengths. So from the sun, these energies are coming in the form of waves. Okay, and then we have the atmosphere in between. Some of these energies or some of the waves can penetrate the atmosphere. Uh, you do not have to give your attendances here. Okay, otherwise it is a distraction for me. So these wavelengths are coming, and some of these waves can penetrate the atmosphere, and then after they penetrate the atmosphere, they come to hit various objects on the surface of the earth. So what are these objects? These objects may be some trees, some buildings, some vehicles, roads, whatever you can imagine, you and I, okay, even tiny objects. So when these wavelengths, they come and hit these particular objects, a part of the wave sometimes is reflected back to the atmosphere. Okay, this is the property of light. Or light is nothing but it's a wave. It's a very small fraction of the entire electromagnetic spectrum. Okay, so then when this reflected light goes back, or you can say the reflected wavelength goes back, it is normally captured by the sensors, which may be mounted on the top of the platforms or the satellites. So when the sensors capture this reflected energy, you can get a fair understanding about the property from where this energy is being reflected. That means in this case, if it is a building, you can get an idea about the quality of the property with which the building is made of. Or if this is a tree, you can get a quality about the growth of the tree. If it is a soil, you can tell about the nutrients in the soil. Many different things, whatever you can imagine. Sometimes it may be getting reflected from the sea surface or the oceans or the waters. In that case, you can tell about the quality of water. And then in this case, it satisfies the concept of remote sensing. That means you can tell about the quality of the building, even you are at the satellite, which is not directly getting in contact with the building. Okay? Or you can talk about the quality, or you can talk about the growth of the trees without directly getting in contact with the trees or the forest. So this is what essentially our modern day remote sensing is all about. We are only talking here in this case about one particular energy which is actually reflected back. Sometimes these energies, when they come and hit these objects, a part of the energy may be consumed or absorbed by the building materials, or sometimes when it happens that they are in the process of coming to the art, there are aerosol particles which are nothing but dust. From there itself, these energies will be scattered back in various directions and they will not reach the surface of the art. So basically there are three kinds of energies. One is reflected energy, as you can see it on the right hand side of the screen. Second one is the emitted energy. Emitted energy is when the energy from the sun is received by the particular object, it absorbs that particular wavelength and it radiates in a different wavelength. So that is the emitted energy. That energy also can be captured by the sensor. And the third one is the scattered energy, the portion of energy which actually has never received or which has never been fallen on the surface of the earth, which has been scattered away from the atmosphere itself. So all these three types of energies can be captured by the sensor, and we have in the process can tell about the properties from where these are either reflected or emitted or scattered. Okay, so the last uh, image on the screen, you see the electromagnetic spectrum that is reflected, or this is coming from the source or the sun. So if you imagine these energies as to be in the form of waves, they have different wavelengths. So what is the wavelength? Wavelength is nothing but the distance between two consecutive peaks or the distance between two consecutive troughs. So this is your basic physics. Okay? So depending on these distance between the consecutive peaks, we can categorize the waves into different categories. Sometimes, if the wavelength is very, 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 very small, for example, if you look at the right hand side of the screen, here if you can see from the cursor, these are the gamma rays. So the wavelengths are very small in terms of nanometers. Nanometers means 10 to the power minus 9 meters. Very, very small. And because the wavelengths are very small, they have extremely high frequency. So wavelength is, or you can see the relationship between wavelength and frequency is reciprocal. It means higher is the wavelength or longer the wavelength, the smaller is the frequency. Or if the wavelength is very small, the frequency is very, 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 very high. So gamma rays, they do have very small wavelengths. On the other hand, they have very high or extremely high frequency. Because of that, they cannot travel too far. They cannot penetrate the atmosphere. They are filtered out by the atmosphere. So they cannot reach us. Then coming to the X-rays, they have slightly larger wavelengths compared to the gamma rays, but even those wavelengths are not enough to penetrate the atmosphere, so they are filtered out. If the wavelength is slightly bigger than that, I'm coming from the right side of the screen, okay? So then you meet the ultraviolet rays. So ultraviolet rays are also having a very small wavelength, which is not quite enough to penetrate the atmosphere. And due to the presence of the ozone layer, they cannot come and reach us. But now, due to global warming and all the greenhouse gases, these layer at the top of the North Pole are depleting, and because of that, some of the ultraviolet rays can come and then hit us. But this is now causing concern because, according to some findings, ultraviolet rays, when they come and hit us, it may be a cause of skin cancer or various types of cancer. So after that, the wavelength is slightly bigger. Then we have the visible light. So visible light is also the kind of wavelength range where you see all the color. So if you look at the screen here, on the right side you see bluish color, and then coming to the middle, yellow, green, yellow, and then further red. So there is this range of color where if the wavelength is changing between 400 to 700 nanometers, you see different colors. If the wavelength is towards 400 nanometer or zero point 0.4 micrometer, the color is more or less extremely blue or dark blue or towards the violet side. Then if you keep on increasing the wavelength, then we see blue, then how to say this is green, then some tints of yellow, and then the extreme end towards the left we have the red. So this range is very small. If you see the range, it only extends from 400 to 700. So the range is basically 300 nanometer range. But within this 300 nanometer range, you see all the billions and billions of colors that exist in nature. So this is very amazing. That means the sensors which are there in our eyes are designed in such a way by the creator or God, if you want to say, that these sensors can capture information which is coming within 400 to 700 nanometer range from the sun. So if the wavelength exceeds a little bit then that we do not see any information. And then even if the wavelength is less than 400 nanometer, in that case also we do not see it. Only between 400 to 700 nanometers you see, and then you capture information by the eyes. Okay. Then we go beyond that visible range, then the wavelength is a little bit increasing. We go to the infrared region. Then slightly more than that, we have the microwave region. And then if you further extend, microwave also goes up to shortwave microwave, then long wave microwaves, so on and so forth. And ultimately, the longest wavelengths that are emitted from the sun are in the range of radio waves. So basically, remote sensing technology, the sensors are designed to capture information like the sensors in our eyes in different ranges, so that the sensors can capture information coming in different wavelength ranges. Sometimes, if the sensors are designed within the visible range, those are known as optical sensors. So remote sensing will be an entirely different branch of science if you are focusing on the 400 to 700 nanometer range. Then these sensors are also designed to capture information in the infrared region, that is the infrared remote sensing. And also microwaves regions are also exploited by the sensors in their design. So basically, depending on what kind of wavelength we are using, remote sensing can be categorized as optical remote sensing or microwave remote sensing or thermal remote sensing, so on and so forth. Okay, so the sensors are interested to capture information either in the form of reflected energy or emitted energy or scattered energy, and in the wavelength ranges of either visible light or infrared or in the microwave region. Okay. That is,
Sir,
yes,
sir, the in between the their sensor and then lens, there is around 2000 kilometer.
no.
So
This is
how
not
could be?
2000 kilometer. These satellites are flown at a height of around 740 kilometers. So this is not 2000 kilometers. There are different
So, sir,
satellites. Okay, so first satellite, there are two categories of satellites. I have to actually highlight you here. One is known as geostationary satellites. So these satellites are flown at a very high altitude, which are mostly used for the telecommunication purpose or for weather forecasting. So these are flown at around 23,000 to 30,000 kilometer heights. Okay, so for that, a different range of technology should be available by the country. Here, in this case, these are known as Earth observation satellites. Earth observation satellites are flown at the height of around 700 to 800 kilometers. So you see the difference. You have 23,000 kilometer at one hand, and then these are at 700 kilometer. So many countries has this capacity nowadays to fly an Earth observation satellite. So our interest will mostly be on the Earth observation satellites. But very few countries can now fly satellites which are known as geostationary satellites at 36,000 or 26,000 kilometers above the Earth. So whatever you were saying, 2,000 kilometers is actually, it's not the fact, but these satellites are flown at 700 to 800 kilometers. Okay, now what's the question?
so, sir, in between there is a lot of layers like ozone layer, which is around in 15 to 20 kilometer. So, do they don't disturb the energy
Exactly.
that
Yes, exactly. So,
reflect back to the sensor?
exactly, very good question. So these layers, you say this may be aerosol particles, dust particles, or any other thing, or different gases which are present in the atmosphere. They influence the property which is actually reflected back to the sensor. So if you are really interested to know the kind of material the building is built with, the energy that is reflected or sensed back at the sensor sometimes has to be corrected. So this correction is known as atmospheric correction, okay, in the image itself. So there is an entire chapter dedicated how many different kinds of atmospheric corrections are there, under what conditions, and where actually the place is situated in the surface of the earth. So if you are really interested to do remote sensing precisely, then you need to know what kind of an atmospheric correction is necessary before you can extract the information of the property of interest. Understood?
Yeah.
Uh, so these all particles, they influence the property of the reflected wave from the building. So you have to correct the signal that is coming from the building. This is known as atmospheric correction. Okay, so another very important thing that you will often come across remote sensing is known as reflectance. So what is reflectance? Reflectance is nothing but a ratio of two energies. One is the reflected energy. That means these energies, suppose once the wave has come from the sun and then it has penetrated the atmosphere, hit this particular building, and then a part of it has gone back to be sensed by the sensor. So this part which is going back is known as RS, or the reflected part. And then if you divide it by the total amount of energy that is incident on the building, Okay, total amount of energy that is coming from the sun and then hitting this building, then you get a ratio. This is known as reflectance. So you see, this is incident energy, this is reflection, and then you divide RS by I, you get reflectance. Reflectance is important because depending on the property, this ratio will change. Property of the building or property of the trees or property of the water or the property of the soil, whatever. That is why you always talk about reflectance in remote sensing. Okay? Now we are coming to a very interesting slide here. So here what you see is a curve or a graph on the left side of the screen. So on the x-axis we have the wavelength, and on the y-axis we have the percentage of reflectance, or you can say it is reflectance. So what is actually this thing is signifying? So if the wavelength is 400 nanometer for the red curve, just you imagine the red curve. What is the red curve? We'll tell you later. At 400 nanometers or around 4 micrometers, we have a reflectance of around, suppose, 2 or 2%. Okay? So that means, as you see in this slide, if you are designing a sensor to capture information of these particular wavelength range around 400, and then the sensor is there in the satellite, and this sensor is capturing information. What kind of information it is capturing? It is giving you an indication about the reflectance of a particular object. Then this red object at 400 nanometer range is showing a reflectance of around 2% or 3%, whatever it's saying. So as you keep on increasing the wavelength, that means according to different sensors in the same satellite, this reflectance of the same object is increasing as you are measuring it in different wavelength sensors, or if you're measuring it with sensors designed in different or increasing wavelengths. Or I'd say if the sensors are being able to capture information coming in larger wavelength, you see the reflectance is increasing. Okay, and then it is going up and up and up and up and up like this. Look at the red, and then beyond 500 to 600 nanometer range, it is showing the maximum reflectance around 15%. That means 15% of the total amount of energy is being sensed back at the sensor. And then again, we keep on increasing the wavelength in which the sensor is being designed. This reflectance is getting dropped. And then finally, it is taking a pattern like this. This is a red color, as you see. So this is known as the spectral signature. And then this is very particular with a particular object on the ground. In this case, this is coming from a pine tree. So you see, you are getting this spectral signature from a distance of 760 kilometers above the earth. That means on the other way around, you can say that from 760 kilometers above the surface of the earth, you can detect a pine tree by simply studying the spectral signature of the particular area. This is the beauty of the subject. This is all about remote sensing. Similarly, had it been a different tree, but the spectral signature is or will be somehow similar to the one that is being shown in the green color. If it would have been far, this color, I don't know what is the name of this color, this bluish color. So all the various kinds of objects on the earth, they have a unique signature, or you can say spectral signature. as the signature is very unique to a particular person. The fingerprint is very unique to a particular person. All these different objects on this art, they have different signature patterns in terms of how they reflect the energy according to an increasing wavelength. So if you know that signature, then you can say for certain or with a fair level of accuracy that it is that particular object, even from the distance of 800 kilometers. This is true for particular objects which are above the earth, and sometimes it is true for objects which are underneath the earth. Or sometimes, if you have some minerals or stones, like the one I see here, it may be kerolite, limestone, muscovite, okay, dolomite. So, all the geology students or someone who is really interested to investigate the rock structure and the minerals on a particular area of the earth, these are the spectral signatures of various, I will say, these are minerals, rocks, and then if you study the image, then you can determine the spectral signature of a particular pixel, a particular area of the earth, and then somehow it falls into one of these categories, and then from there you can draw the inference that these are either limestone or dolomite or chloride, whatever. So you have to have the expertise or subject expertise of geology, or in this case, you have to have the subject expertise of botany. Plus, you also need to know about remote sensing. That is why remote sensing is known as a vertical technology. Sorry, horizontal technology. That it crosses all the disciplines, and it is becoming increasingly important for everybody in every field to study about remote sensing. Okay, so if you are a student of geology, if you're a student of civil engineering, and you have an added advantage of remote sensing as a tool, then you are better positioned in terms of acquisition of knowledge. Okay. So later on, I'll just be highlighting the same thing. The spectral signature of some of the very common things which we often come across are like this. So here on the slide on the right hand side, you see clear water. Clear water is why we see clear water as blue, because in the blue range around 400 to 410 nanometer, it shows the highest reflectance or maximum amount of energy is being reflected during this range. And in other wavelengths, this energy is absorbed by the chemical properties of the water. So here, if you look at the graph, in the blue range, around zero point 0.4 up to maybe here, you see the blue color graph, which is showing maximum reflectance around 8. This is 10, now around 12. So that means around 12% of the emitted energy is being reflected. And then if you keep on increasing the wavelength, or if you're trying to sense the amount of energy in a bigger wavelength range, it shows a drop. That is why we see clear water in blue color. That means in the blue range, maximum amount of energy is normally emitted. So why we see something of a particular color? That means on the particular wavelength, you have the maximum reflectance. If you are wearing a red shirt, that means the chemical properties of the object due to the pigment or whatever pigment you are using, they have a chemical property. So at the molecular level, at the chemical level, they are interacting with the wave that is coming from the sun, and then it is resulting in such a fashion that in 700 to around 650 nanometer, maximum amount of energy is being reflected. That is the red range. That is why you see it as a red color. Okay, so if you again go back to clear water, you see the curve pattern like this. If it is turbid water, that means if the water has some level of sediments, then we see an increase in the green range. Again, this increasing is continuing up to the red range and then suddenly it drops. So we have a dominance of green and red that is resulting in the yellow. No, it's the yellow range that is dominant. Then again, the vegetation or whatever shrubs, or trees, or forest cover, you see this green graph. There is a drop in the blue range. That's why no trees you see it in blue color. What is happening in the green range? The reflectance is increasing. That is why we see all the tree leaves in green color, right? And then in the red range, it is going down. But there is very important thing what is happening in the near infrared region. In the near infrared region, this amount of reflectance is shooting up much, much, much more than what is in the green range. That is for the trees and the leaves. This is happening because of the properties of chlorophyll which are there in the tree leaves. But unfortunately, our naked eye can only see up to 700 nanometer. That means we cannot see beyond this red range. Even there is a very sharp rise of reflectance values in the near infrared region because our eyes cannot see anything in near infrared. So we do not, or we miss this information. But the sensors or the artificial sensors which are on board the satellites, they are designed, or sometimes they are designed, they can be designed so that they can capture this information in the near infrared region. Okay, so sometimes if you are building a sensor in the blue range, it can be called the blue sensor, which is be capable of capturing information to 400 to suppose 420 nanometer. Then 430 to 450 nanometer, you are creating another sensor. It will be able to clear called the green range and then red range, and then also you can create or build one sensor in the near infrared region. So these satellites, they do have different sensors, or we can say bands, which actually are capable of capturing information that is being either emitted or reflected or scattered in various bands. So in a particular remote sensing image of a particular pixel, if you see this spectral signature, then in general you can say that this is coming from an area which is dominant of trees or tree cover. Or if it is a magenta color like this is of the bare soil. If it is a turbid water, it could be something like this. If it is a clear water, it would be in dark blue color. Or the graph is shown in the dark blue color. Okay, I think you are bombarded with too many information. This is too much of a science to be covered in one or two chapters. But anyway, I hope I can make these things interesting. And we have maybe another 2 or 3 classes to finish off this syllabus. And hopefully I'll be talking about the other aspects of remote sensing in the other classes. Okay, I will not go into too many details right now because we may lose interest. Okay, so anyway, we are finishing off our times. If you have a question, then you can ask, or we will.
Sure.
Yes.
Can you tell about little bit about satellites?
Sure. So satellites, I will like to tell you in the next class because if I start talking about the satellites, I'm not stopping in between. So that will actually just make the lecture very uninteresting. So how about the next class? I'll talk about the satellites.
Okay.
Okay.
Okay. Now, sir, type of satellite
Uh,
maybe depends using different
sure.
geo
Sure.
using different.
Definitely. Yeah. I'll talk about the satellites in the next class. So in fact, it is there in the syllabus also. We have the different remote sensing data acquisition platforms and sensors. So I think we can elaborate on that. Okay. Oh, by the way, the next class I will take today around 2:15 for a disaster preparedness class. See you then. Nice. We are almost finishing the time. That's why I would like to wrap up. Okay. Okay.